and I would like to present our programs DC-Geotex and DC-Gabion, which are part of the program group DC Foundation that you can see here for the analysis of different types of walls, foundation pit walls, cantilever walls, soil nailing, slopes, piles, footings, groundwater lowering, and so on. DC-Geotex and DC-Gabion are two products within one program, and you can purchase one single of these products or both together at a reduced combination price. So DC-Geotex is intended for the analysis of reinforced soil with geosynthetics. And this reinforced soil block may have a front wall made from gabions or from stack stones and so on. And on the other side, DC-Gabion is a program designed for stack stone walls alone without geosynthetics, stack stones, gabions, and so on, and may as well support freestanding walls like noise protection walls, for example. So if we start a new project, we have the most important functions here on the icons at the left. And first we have the selection of the analysis standard. And there are several older standards from Germany, from Switzerland, from Great Britain. And we have Eurocode with a number of countries predefined. So the national annex of Germany, of Austria, France, Great Britain, Italy, and in this program as well for Romania and Netherlands are predefined and can be selected directly. So you have all the parameters, all the safety factors, and where to use which safety factors predefined in this dialog without changing this by hand. Now, first we can create the ground surface. This may be here some arbitrary course of the ground. Until we end this input with the right mouse button. And here we can define the soil type. And we may as well use a parameter suggestion. So if you have the same types of soil again and again, you don't have to enter all the parameters all the time and just select some sand, for example, with a friction angle of 35 degrees, no cohesion, and the unit weight of 20. Now this is our basic ground surface, and now we can define different soil layers which may have an arbitrary shape. As a difference to DC pit, for example, we don't have the classical calculation of earth pressure, but we have earth pressure calculation according to Kuhlmann, and this means we can have here an arbitrary shape of the soil layers which can be defined. Now here this could be some silt, for example. We can have a distribution of water level. And as you see here, as long as some icon is pressed, you're still in input mode. This means that if we click here, we create a new soil layer. If we end this with the right mouse button, there is no icon pressed anymore. We are in edit mode. This means with the double click, I can change every parameter which was defined before. I can change the soil layer, the friction angle, the cohesion, and so on. Then for DC-Geotex, we define the shape of the reinforced soil mass. And we can define this on the ground here, on top of this ground surface, or we cut it out of the basic ground model. So with this kind of shape, for example, this should be our reinforced soil mass, which is cut out from the original ground surface level. Here, this could be some gravel, for example. And we can define to calculate the required length of the geosynthetics layers. or we calculate the predefined lengths of the geosynthetics to know if we have the a sufficient safety level for this calculation. Now this is our reinforced soil mass, and now we can define the geosynthetics levels or layers. So for example, we start here at the base of this shape, and we can define the type of geosynthetics with all the reduction factors, with the tensile strength of the geosynthetics. And again, we have parameter suggestions, and here we have many products predefined with all their values. This may be Comtrack, Incagrid, Fortrack, Geolon, Miragrid, Polyfield, Secogrid, Stavelinka, Tensor, and so on. You see quite a large number of different types that you can select here. And here we have first the strength of the geosynthetics, the characteristic value of the strength, which is reduced by a safety factor and reduced by a number of reduction factors from A1 to A5 for different effects. For example, the time stability of this geosynthetics, the consideration of placement damage, working environment, and dynamic loads. And we have a friction factor, lambda value, for the friction between the geosynthetics and the soil. Now, for some of the reduction factors, there are different values, depending, for example, of the grain size diameters of the filling material, or depending on the time for which the construction is intended, for 50 years, 120 years, and so on. And we can select which value here to use. So these reduction factors are transferred to the dialog, and you see, or you will see later, that the characteristic strength of 88 kilonewton per meter is reduced by the different reduction factors here and by the safety factor for the stability of the total construction. Now we mostly have quite a number of synthetics layers, so we can add, for example, 10 layers with a difference of 50 centimeters each. And this way, this reinforced soil mass is filled with the geosynthetics layers. And first, these are wrapped around. You see that the end of this geosynthetics layer is fixed here by this wraparound length. Now this soil block may have a front wall. So we can define this at this edge at the front. And here we can select concrete precast elements, concrete panels, concrete stack stones, gabions, natural stone blocks, and so on, quite a number of types. Let's take gabions here. And these blocks may be defined here with a thickness, with a height of one section, unit weight, friction coefficient, which can normally be about 0.6, for example. So this is the friction between the different blocks. Our geosynthetics construction can be wrapped around, which is shown here as the first option. In this case, there is no earth pressure loading the wall itself, but it is kept about this wraparound length. The geosynthetics may be fixed at the wall. This means that they act with a complete strength. This is a maximum force that can be transferred to hold the front wall. Or they may be inserted into the wall, which means that we have some friction between the different blocks. And this would be the coefficient for the friction between walls and geosynthetics. So the load from the different blocks multiplied by the friction coefficient gives the maximum force which can hold the earth pressure on the wall. So we have our gabion wall here, and you see, if we look at the print preview, this part of the ground surface is cut out, and we have here the reinforced soil block placed on the ground. Now we can define different loads, concentrated loads, distributed loads, for example. Here load case 1 with a vertical load of 20 kilonewton per square meter. This should be a live load in a permanent situation, and we have the safety factors predefined for the load. We can predefine a certain failure unit to be checked. We can have a fixed point for the slope stability, which we don't need by default. And then we can calculate this construction here. And you see that all these different soil blocks are calculated for the internal stability. We are looking for the block with the least safety, the critical safety for this construction. And these geosynthetics layers may as well be lengthened if they are not sufficient. And up to this time now, it's still a sufficient length. They are not lengthened yet. So this is quite a complex calculation, which does a large iteration for all the possible blocks, which might be the critical failure plane. Here you just saw that there was a little lengthening of the geosynthetics. Now we have the iteration of the friction circle. These are the centers of the slope stability circles. And then the analysis is finished. And we can switch through the graphics alone or the complete results. And here you see first all the input parameters with the soil that we defined, with the lines, limits of the soil layers, the type of facing from gabions. We have the loads, we have many different safety factors. And then we have the calculation for the internal stability for the critical sliding mechanism, where we need a utilization of less than 1.0. So the check is fulfilled for the internal stability. And here we see the different geosynthetics layers that we defined. We have the type with the different reduction factors. We have the strength parameters with the factor of safety for the material. And so you see with a critical characteristic strength of 88 kilonewtons per meter, we have a design value of only 26 because we have many reduction factors and safety factors that reduce the characteristic value. Now for the external stability, we have an overturning verification. We have the safety calculation against sliding. We have a settlement calculated for this reinforced soil mass. The bearing capacity analysis below this block. We have the slope stability calculation, which is as well fulfilled here with a utilization of less than 1. And finally, the verification of the facing, which means for every block that we defined, we have an additional check if there is some sliding problem, if the force of the geosynthetics, the support force, is sufficient to take the loads from earth pressure on the wall. And here for the overturning between the single blocks, there is no problem as well. So all the verifications are fulfilled. On the next slide, we have the safety calculation for the gabion wire, which means from the loads transferred through the gabion wires, we calculate which wire diameter we need. So you see that about 2 millimeters of wire diameter are sufficient. with a distance of 30 millimeters between the different wires. So we can define this distance and get the required wire diameter as a result. And finally, the graphics, you see here the critical friction circle. You see the critical block here for the internal stability, and you have the most important results, the utilization of the internal stability, sliding, bearing capacity, and friction circle. And finally, the loads from earth pressure on the wall, where the geosynthetics are the supports, and they define these section forces which are used for the verification between the different blocks. And in this case, all the verifications are fulfilled. So this is a part of DC-Geotex where we have a reinforced soil block with geosynthetics. And the other project, or the other part of the program, is DC-Gabion. Here we have only one slight difference for the input. If we have defined our ground surface here, this should again be some sand, for example. Here we don't define a reinforced soil block, but we directly define the kind of wall. So this is for the calculation of, for the verification of the wall only. So this wall should be here along this ground surface line. We have again these different types of walls, of stackstone walls and so on. And in this special context, where we define the wall directly, we have as well an option to define all the single blocks with different thickness, for example. So by default, we have a wall here as we had it before with different blocks. And then we can edit this wall and here go to the section 1 of 7, for example. And we can define that here we have a wall thickness of 80 centimeters, for example. The second block 70 centimeters, the third one 60 centimeters. And we may have a foundation below this wall, which should be with a width of 1 meter, for example, height of 60 centimeters. And this should have some distance from the axis, for example, 20 centimeters to the left. And this way you see the footing below the wall, and you have different thicknesses of the different blocks of the wall. So this is one option which is not available in DC-Geotex, where you have a constant thickness of all the wall elements. And here in DC-Gabion, you can change any single element, and you may as well shift them to a certain distance of the axis. For example, here the section 1 should be with a distance of 10 centimeters. So this is going somewhat to the left, and you can create all the different positions of the blocks of the wall. We can again have the loads here on the ground, the live load, for example, and calculate this example number 2. Well, I had this load should be only on the wall or within the ground. So this was just a little conflict here for the position of the load. And we have again the calculation of the external stability. So for the total loads, we have the check of the overturning, safety against sliding with an utilization of 88%, bearing capacity with 54%, slope stability with about 80% utilization. And here we see that within the wall, there are not all the verifications fulfilled. Sliding is nearly okay here with about a little more of 1. But here within the wall, we have a problem of overturning. So the eccentricity of the load is a little too high. And we can see this here in the graphics. If we make a little larger zoom to see the wall in detail, we have in red the center line of the different blocks. We have in blue the limits for the eccentricity for permanent loads and for live loads. And you see that here at certain positions, if we have only permanent loads, we are outside of this core here. So we have an eccentricity which is a little too large. So in this case, we would need a little larger wall with a larger width to fulfill the overturning verification. So this is a wall stabilizing the slope. And in addition, we have the option to create or to analyze freestanding walls, for example, noise protection walls. So our ground surface might be just horizontal, for example. We have some gravel here, and now the wall could be just here some vertical construction made from gabions with a certain thickness of the wall. And then we can define, for example, horizontal loads. This should be some wind force, some wind load. Horizontal with a value of -10. This is a live load. So we have this horizontal load here on the wall. And now we can check if this is, if here the stability is fulfilled. And for example, for this small wall, there is a problem of overturning. Here the verification against tilting of all the single blocks is not fulfilled. And we see this again here in the graphics. We see that the forces are running outside of the wall. So this wall, which is very, very small, very thin, would not be stable. And we can then change the different blocks. For example, we have a thickness of 1.20 meters for the first block, 1.10 meters for the second one, 1 meter third one, and so on. So we can define all the different blocks with different measures, with different thickness. Now we have a much larger wall. And this is calculated quite quickly. So again, these verifications are not all fulfilled because we just have a single standing wall without the support, and there should be some inclination of the wall or larger elements to have all these verifications fulfilled here. Okay, so far for the different types of the wall, we have some more functions for creating or for editing the graphics that we have in the program. Here, this is some list of graphics functions. We can add here graphics, we can add text, we can have measurements. We can as well import DXF files. So you have graphics in the background and use it for the construction of the soil layers, for example, or define of the different layers. And we support all the layers of the DXF, for example. You can switch on and switch off different graphics layers in this construction here.